And we're off. Okay, last chapter. Yay. We're going to talk about gases. Let's see that. Okay, let's look at characteristics of gases. They assume both the shape and volume of the container. So whatever you keep it in, that's the shape it is, and whatever volume. Gases are compressible. That's what you hear about compressed gases all the time. The density of gases are much smaller than those of liquids and solids, and highly variable depending on temperature and pressure. Okay, some of these equations we're going to go through, if you just think about them, they're just really mathematically relating to what pretty much is common sense to us. Gases form homogeneous mixtures or solutions with one another in any proportion. So air obviously is a mixture of nitrogen, oxygen, carbon dioxide, water vapor, some other stuff. It's homogeneous. You don't change the composition as you move from one area to the other. Some things we have to define. Pressure is defined as the force applied per unit area. So the SI unit is the Newton. So Newton is defined as 1 kilogram times a meter per second squared. That's an area of force, measured force. SI unit of pressure is the Pascal, which is 1 Newton per meter squared. And 1 Pascal is 1 kilogram per meter times second squared. So Newton is if you take a kilogram and accelerate it meter per second squared. Okay. Standard atmosphere, which is the pressure at sea level, is 1 atmosphere. Okay. Don't worry about the Pascal. We can also look at it as a millimeter of mercury. That's a barometer measurement, so when you watch the weather on TV, they usually refer to so many millimeters. We're talking about millimeters of mercury. Torr, they renamed the millimeter of mercury to torr, name of Torricelli, the inventor of the barometer. And bar, which is the same order of magnitude as an atmosphere, but a decimal multiple of pascals. Really what we're going to be concerned of is 1 atmosphere is 760 millimeters of mercury. And 1 atmosphere is also 760 torr. Torr and millimeter mercury are the same. All right, here they're looking at a column of air calculating the pressure. We don't mess with all of that. But this is how a barometer works. You have mercury in a pan, and you have a sealed tube. And if you're at sea level, atmospheric pressure, 1 atmosphere, the pressure is pushing down on mercury and pushing it up inside the tube. So at sea level, the distance from the mercury to the top of the tube, with mercury to the top of the tube, is 76 centimeters or 760 millimeters of mercury. So that's equal to 1 atmosphere. So if you go down to Wilmington and stand on the beach with a barometer, that's what it will read at sea level. It was originally defined as the pressure that would support a column of mercury exactly 760 millimeters high at 0 degrees Celsius at sea level. So how do you predict weather with that? Well, it turns out you hear low pressure system coming in. Low pressure system, there's not as much air pushing down. So the level in the tube falls. And you hear people talk about dropping barometer. barometer is dropping. Low pressure is associated with rain, tornadoes, hurricanes. So if it drops very rapidly, get out, hunker down, seek cover. And that means there's high winds, low pressure coming. High pressure, you have more pressure pushing down on the mercury, goes up higher in the tube. So we hear about a rising barometer. That's associated with fair and sunny weather. So if you're on TV, you're watching TV and the weatherman says the barometer is rising, that means better weather's coming. And if it says it's falling, it means worse weather. Rain. If it's falling rapidly, that is usually associated with things like tornadoes, hurricanes. So the pressure exerted by a column of fluid is given by the pressure using the height, density times the force of gravity. So what we use to measure these is a manometer. So here we can measure pressures other than atmospheric pressure. So here on the left, we have a system which is sealed, and there's a gas in the flask on the left, and we seal off the system. So the gas comes in and pushes down on the mercury and pushes up. So the difference between the mercury level on the left and the right, the height, is from the pressure of the gas. Now the one on the right, you see the tube on the right is open at the top, so it's not sealed. So additionally, you have the gas pressure pushing down on the mercury on the left side of the tube, and on the right side of the tube you have atmospheric pressure pushing down there. So there the pressure of the gas is the pressure of the height of the tube plus the atmospheric pressure. And this one is just the height of the pressure because it's sealed at the top. There's no atmospheric pressure pushing down. So, an example, calculate the pressure exerted by a column of mercury 70 centimeters high. And they want it in pascals in an atmosphere. The density of mercury is 13.5951 grams per cubic centimeter. I'm sure y'all knew that. So height must be expressed in meters, and density must be expressed in kilograms per cubic meter. Conversions. Well, the height we changed to meters, so it's 0.7 meters. Density in grams per cubic meter, so we changed grams to kilograms, and centimeters cubed to meters cubed. And if you do that, you end up with 1.35951 times 10 to the fourth kilograms per meter cubed. And G, the gravity is 9 force of gravity years. 9.80665 meters per second squared. So pressure is equal to the height, density, G, and we get 9.33 times 10 to the fourth kilograms per meter times second squared, 9.33. And it should be 9.33 times 10 to the fourth here, not. So 9.33 times 10 to the 4, that's pascals, and converted from pascals to atmospheres is 0.921 atmospheres. We're not going to bother with a lot of that. So from that we get into gas laws. Start off with pressure and volume relationship. Now, if we just think about this as a cylinder, before we even get to the page, let's just think concepts. So here I have a cylinder, and it has a certain volume, call it V1, and a certain pressure pushing down, P1. So I increase the pressure, and I'm going to call it P2. What's going to happen to the volume? It's going to decrease, right? I'm going to push it down. Give me a new volume. right? Putting more pressure, you're squeezing it more. Okay? So these things are related. As one goes up, the other goes down, so that's an inverse relationship. Well, it turns out that pressure times volume always give me some constant K. Okay? So the pressure times volume is always going to give me a constant number. So here I can say P1 V1 is going to give me a constant K, right? P2 V2 is going to give me the same constant K. So I can set them equal to each other. So P1 V1 is equal to P2 V2. That's Boyle's law. So the volume is indirectly related, inversely related. So you can see PV K1 at constant temperature is going to be P times V is always going to equal a constant at constant temperature. So if I plot volume over versus 1 over pressure, I'm going to get a straight line. So P1 V1 is equal to P2 V2. That's our first gas law, Boyle's law. So here we have our skin diver. We do a lot of skin diving here. Takes a breath at the surface, filling his lungs with 5.82 liters of air. What volume will the air in his lungs occupy when he dives to a depth where the pressure is 1.92? Well, before we even do any calculations, what are we doing with the pressure? Increasing it. So what do you think we should happen to the volume? Decrease. We're squeezing it. So right away we know whatever we end up with should be less than the initial volume. So P1 was 1 atmosphere. V1 was 5.2 liters. We know that's got to equal to P2, 1.92 atmosphere, times V2. Now we just solve for V2, which would be 1.00 times 5.82 divided by 1.92. V2, and I'm too lazy to do it, so I'll just skip to the next page. 3.03 liters. That's all there is to it for Boyle's law. That's assuming we hold temperature constant. So we all set with Boyle's law? We okay with that? Now let's change our thinking a little bit. So I have a balloon, put air in it. I heat the air in the inside of the balloon. What's going to happen? It expands. So as the temperature of the air goes up, the volume of the balloon increases. That is a direct relationship. As one goes up, the other goes up. So I can say the initial volume at an initial temperature would give me the final volume, final temperature, V1 over T1, and I think this already. Temperature volume. Volume is proportional to temperature. And if we plot volume versus temperature, we get straight lines. So V1 over T1 is equal to V2 over T2. The thing you have to remember here, when we talk about temperature, we're talking about Kelvin, not Celsius. Kelvin temperature, remember back at the beginning of the semester, is related to atomic motion, molecular motion, particle motion. Celsius isn't. When we're talking about gas laws, we're talking about atomic motion. And this is a constant pressure. So here you have a sample of argon gas that originally occupied 14.6 liters at 25 degrees Celsius. You heat it to 50 degrees Celsius at constant pressure. Well, you're heating it, so you expect the volume to be increased. So now you've got to identify T1 is 298.15. Remember, we've got to go from Celsius to Kelvin, so we're going to add 273.15. V1 was 14.6, and T2 is 323.15. So V2 is V1 times T2 divided by T1. Just rearranging the equation. Put the numbers in. V2 is 15.8 liters. The volume went up, just what we thought. So I encourage you, when we get to do these problems, to think about essentially what happens, so that when you do the calculation, you should know that you get, in this case, an increase in the volume, your number should come out bigger. If it comes out smaller, you did something wrong in your calculation. You just set up the problem wrong, or you did it upside down, something. So, I'm going to pose this question to you. I have a certain amount of air in an enclosure. Okay? A fixed amount of air. I heat that air. What happens to the volume of the enclosure? Yes. It expands, right? Okay, so it expands. But I have a fixed amount of air. So what happens to the density of that air? It what? It decreases, because density is mass over the volume. I didn't change the mass, but I did increase the volume. So density's gone down. So how does that air inside the enclosure compare to the air outside the enclosure? The density went, it's less. So the density of the air inside the balloon compared outside is going to make the balloon. Yeah, that's the principle behind Santa Fe, New Mexico, the hot air balloons. That's why a hot air balloon works. You heat the air up, the balloon expands with the same amount of air, the density goes down, density goes down, the balloon goes up. Which is why they always have the burners underneath there. So you turn the burner off, the air cools, density goes back to normal, the balloon comes down. Hopefully not too fast. Okay. So let's take another example of that. So I have air over the ocean, and it hits land. Now land is radiating heat, so the air heats up. What happens to the air? It rises. And what do we call that? It's front, but what do we call that? When front comes through, what do you experience? Front came through this morning. If you're standing outside, well, temperature change along with that. Wind. That's what makes wind. I know you guys get there eventually. So we did Charles's law. Avogadro's law. Well, guess what? I have a balloon of a certain volume. I blow more air into the balloon. What happens to the balloon? It gets back. Well, pops. There's always okay. It gets bigger. All right. So I mean, this is stuff that you've been doing since elementary school. You're blowing up balloons. So Avogadro's law is directly, it says V1 over N1 is equal to V2 over N2, where N is the moles. Basically just says the more you put in, the bigger the volume. And you should tell me, well, duh, I've been blowing balloons up since I was 5 years old. I know that. So here we have, we're making ammonia. 3 moles of hydrogen plus 1 mole of nitrogen gives me 2 moles of ammonia. So I have 3 volumes plus 1 volume. I start with 4 volumes. If I do the reaction, I go to 2 volumes. So what actually happens? So I had a certain volume, V1, moles that I have at the beginning. Total, 4. At the end, I had how many moles? 2. So if I had this in the container, what would happen to the volume of that container? No, half as much. So it would shrink. So if I combine 3 liters of nitrous oxide and 1.5 liters of oxygen, and they react according to that balanced equation, what volume of NO2 will be produced, assuming that the reactants and products are all at the same temperature and pressure? Okay. Apply Avogadro's law to determine the volume of a gaseous product. So let's look at it. According to the balanced equation, the volume of NO2 formed will be equal to the volume of NO that reacts. So 3 liters of NO2 will form, because we started with 3 liters of NO. What happens if we're going to vary the pressure, the temperature, and the volume? Well, we can put these top 2 equations together and get P1 V1 over T1 is equal to P2 V2 over T2. That's the combined gas law. Basically, just as we change all 3, we know what's going to happen. And if you look at this combined gas law, obviously if we keep the temperature constant, this falls out, we have Boyle's law. If we keep the pressures constant, these fall out, we have Charles's law. So basically all you have to do, that's for a fixed amount of gas, where the number of moles don't change. So basically all you have to do is know how to rearrange the equation. If I said solve for T2, what would T2 be equal to? Rearrange the equation. Got it? What do we get? T2 is equal to what? This is where you guys speak up.
Is it P1, B1? I don't know, I look like backwards.
Anybody? Yeah, it's actually P2 V2 T1 divided by P1 V1.
Okay,
Yeah. That gives a lot of people trouble. So here we have this kid who releases a 6.25 liter helium balloon in the parking lot of an amusement park, where the temperature is 28.5 degrees Celsius and the air pressure is 757.2 millimeters of mercury. What will the volume of the balloon be when it has risen to an altitude where the temperature is minus 34.35 degrees Celsius and the air pressure is 366.4 millimeters of mercury? And part 2 of the equation is how long will he cry after his father smacks him for releasing a $5 balloon in the parking lot? Okay, no. So you can set up, look at the two temperatures, we convert them to Kelvin, T1 and T2. So V2 is equal to P1, T2, V1 over P2 times T1. Sure, everybody has that? Or take my word for it. Plug in the numbers. V2 is 10.2 liters. So the balloon did what? Expanded, didn't it? They actually had a competition among community colleges last year where they went out to somewhere around Charlotte, Hickory, somewhere, and they had to launch a helium balloon, and they had a little payload, and they had with cameras and parachutes. And see if you could get it to travel the farthest. So obviously as the balloon goes up, the air gets colder, pressure goes down, the balloon expands, it's going to reach to a point where it pops. When it pops, the parachute comes out, and well, there was one team, geology instructor told me from Pitt Community College that it actually landed in Goldsboro. So you figure it went from Hickory, Hickory to Charlotte, all the way to Goldsboro. And they had a tracking device and they were going along board and tracking this parachute coming down. Obviously it went very high in the air. Take that long to come down. The ideal gas equation, I'll tell you right now, Pivner. You remember Pivner? PV is equal to nRT. Okay. R has different values. It's an ideal gas constant. The one that we're going to use is 0.08206 liters times atmosphere over mole times Kelvin. R. But it can have different values depending on what you're going to do. And if you go on to 152, you're going to use R as 8.314 joules per K per mole. You may use 1.987 calories per K when you get into thermodynamics. But for now, the gas laws are 0.08206. The volume of 1 mole of an ideal gas at 0 degrees Celsius in 1 atmosphere conditions, that's known as the standard temperature and pressure, STP. 0 degrees Celsius, 1 atmosphere of pressure. The volume turns out to be 22.41 liters. It doesn't matter what the gas is. 1 mole of any gas in those conditions will occupy 22.41 liters. Because you can look at the equation, nowhere does it ask you what gas it is. You have 1 mole of it. There's the R, there's the temperature in Kelvin, and the pressure, 1 atmosphere. It's always going to come out 22.41. So calculate the volume of a mole of ideal gas at room temperature and 1 atmosphere. So we know we have 1 mole. There's the temperature, 298.15, and the pressure of 1. Now, because the pressure is in atmospheres, we're going to use R is equal to 0.8206 liters. If I gave you the pressure in millimeters of mercury, you convert the millimeters of mercury to atmospheres by dividing it by 760. So here you just do the same thing, the volume. So at room temperature, a mole of any gas will occupy 24.5 liters. Questions? So these are all different ways you can rearrange the equations. You can use molarity, you can use density. If we had time this semester, I don't know why we didn't get to it, but usually in the lab we calculate the molar mass of a volatile liquid by using the ideal gas law. So CO2, we use in fire extinguishers because its density is greater than that of air. So CO2 smothers the flames. Air has a density of approximately 1.2 grams per liter at room temperature and 1 atmosphere. Calculate the density of CO2 at room temperature and 1 atmosphere. So we look at the molar mass is 44.01 grams per mole. Because we want to compare its density to that of air. So we want it in grams per liter. So think about it, a mole, well, we can go density is equal to pressure times molar mass over RT. And do all the calculations, 1.8 grams per liter. So you could have also used the ideal gas equation that said P V equals nRT and V is equal to nRT over P, and T would have been the room temperature, and that would give you the volume of liters. And for 1 mole, it was 44 grams per liter. 44 grams per molar mass. You just divided it by the volume and got the same answer. If I look at this equation, carbon monoxide plus oxygen gives me carbon dioxide. What am I saying? If we look at the stoichiometry, I said for every mole of oxygen, I need 2 moles of carbon monoxide. Or for every liter of oxygen, I need 2 liters of carbon monoxide. Or for every milliliter of oxygen, I need 2 milliliters of carbon monoxide. So if I have 65.8 milliliters of carbon monoxide, I need 32.9 milliliters of oxygen. Just like we do normal conversions. So here I have solid sodium plus chlorine gas given us sodium chloride. So grams of A to moles of A for sodium, we divide by the molecular weight. We can get the moles of chlorine by doing the conversion. So now I get the moles of chlorine. Then the volume is equal to, just what we said, nRT over P. Taking the moles of chlorine, multiplying by RT over P, I can get how many liters of chlorine gas to put in there. Everybody follow that? Yes, no, no. Okay. Let's look at it step by step. I'm taking sodium, plus chlorine, 2 and 2. So there's my balanced equation. So, if I'm starting with grams of sodium, I want to know how much chlorine to add to do the reaction. So remember our stoichiometric roadmap, grams of A to moles of A, moles of A to moles of B, but I'm not going to grams because I can't weigh out chlorine gas. Well, I can, but it's a lot easier to know the volume. Once I get to moles of B, I can go to volume. So I start with grams of sodium to moles of sodium, 23.3 grams of sodium, right? That converts it to moles of sodium. Now I go moles of A to moles of B. I use the coefficients, right? Moles of Cl2 over moles of Na, 1 over 2. So now I got the moles of chlorine. I could go to grams of chlorine, but that's kind of inconvenient. But now I have moles of chlorine. If I have PV equals nRT, I know this. V is equal to nRT. I know this, I know this, I know this, and I know this. I calculate the volume, which would be equal to that number of moles. I say, okay, I got 23 grams of sodium. I got 1 mole of sodium. I'm going to add half mole of chlorine, half mole, whatever that comes out to be, what temperature, so many liters of chlorine gas to that. That's going to give me my reaction. In practice, I'd probably add excess chlorine gas to make sure all the sodium is reacted. But it's easier to get rid of the chlorine gas. Just open the pressure valve and the chlorine gas will come out. Here we have sodium peroxide. It's used to remove carbon dioxide and add oxygen to the air supply in spacecrafts. And there's a reaction. What volume in liters of CO2 at STP will react with a kilogram of sodium peroxide? So we're going to do the same calculation, same steps. So the molar mass of sodium peroxide tends to be 77.98 grams per mole. So we start with 1,000 grams, we said 1 kilogram. So we end up with 12.82 moles of sodium peroxide. And it turns out that it's a 1-to-1 ratio, or 2-to-2. So we end up with 12.82 moles of CO2. So we do V, this calculation, 12.82, and there's R, which is constant, and there is STP, 0 degrees Celsius, 273.15 Kelvin. Turns out we need 287.4 liters of CO2. Or conversely, it'll tell us if I want to recycle that CO2, especially on the spacecraft. Think of Apollo 13. I need 77.98, I need 1,000 grams of sodium peroxide. We can also determine the amount of reactant consumed using change in pressure. So you know N is equal to P times V over RT, just rearranging this equation, PV equals nRT, N is equal to PV over RT. We take, which is equal to P times V over RT. So the change is in N. If I change the number of moles, I'm going to change the pressure, assuming a constant volume and temperature. So if I have a container, solid container, not a balloon, so it's not going to change the volume. I keep it at the same temperature and I do a reaction, the pressure inside is going to change. So if the change in the number of moles goes down, what's going to happen to the pressure? Yeah, it's going to go down. Again, changing the number of moles goes up, the pressure is going to go up. Think about that conceptually. So here I have a sealed container, okay? Maybe with a valve on it. I add more stuff to it. I'm increasing the number of moles. I've got more stuff in there. Pressure, by the way, in the container for gas is due to the particles hitting the wall. So that's causing pressure. If I increase the number of particles by increasing the number of moles, more we're going to hit the wall, the pressure is going to go up. All right, here's another way they get rid of CO2. Use lithium hydroxide, and this is actually the example or the thing they used if you watch Apollo 13. You saw the movie, that's where the lithium hydroxide really kind of cobbled together an apparatus to get rid of the CO2. If the CO2 levels get too high, you pass out. Eventually you die. So this is they're using a submarine. So the submarine has a total volume of 2.5 times 10 to the 5th liters. Obviously, it's a big container. The pressure is a little bit less than atmospheric pressure. The temperature is room temperature. If the pressure in the submarine drops to 0.981 atmosphere as a result of carbon dioxide being consumed, how many moles of CO2 are consumed? Well, if we look at the equation, how many moles are on the right total? I mean on the left. I mean total on the left. 3. And on the right there's 2. So as the reaction goes, the number of moles is going down, so the pressure is going down. The change in pressure, that should say change, not that little arrow. So change is 7.9 times 10 to the minus 3 atmospheres. The volume was 2.5 times 10 to the 5 liters, and the temperature was 295. And again, because we have pressure in atmospheres, we can use R as 0.08206 liters atmosphere K mole. We can use the change in the moles of NaCO2 is the change, remember, it was the change in N is equal to the change in P times the RT over V. No, I did it wrong. D over RT. So there is the volume for the submarine, RT, and it turns out 81 moles of CO2 were consumed. So why would that be important to know? Well, there's so much oxygen and you're building up CO2, but you only have so much lithium hydroxide for it. So after a while, you say, well, if I use this much CO2, I've used up this much lithium hydroxide. And if you get to the point we run out of liquid hydroxide, you can't use up the CO2 that's going to build up in the submarine. And so you've got to surface and replenish that, take care of that. So using a combination of stoichiometry and the ideal gas equation, we can calculate the volume of a gas that would be produced in a chemical equation. So airbags in your car are inflated when the collision triggers the sodium azide, highly explosive, in your car. Essentially, it's a mini explosion that blows up your airbag. And there's the equation for it, and it's the nitrogen that blows up your airbag. So driver's side airbag contains about 50 grams of sodium azide. So volume of N2 gas that would be generated by the decomposition of 50 grams of sodium azide at 85 degrees C in 1 atmosphere. Okay. So you have the moles, we figure out the moles. So we start off with 0.769 moles of sodium azide. And we do the conversion 3 to 2, so we end up with 1.15 moles of nitrogen. And then we use the V is equal to nRT over P, 33.9 liters of N2. And that's how much nitrogen fills up an airbag when it explodes. And I'm going to stop there because we have time to review for your tests later on today.